All right, let's dive into a real classic physics problem today. It's one of those that seems a little counterintuitive at first. We're going to figure out how the chaotic, always changing motion of a planet in orbit somehow has an energy that all comes down to just one single number. So let's get into it. So, where are we getting this problem from? Well, none other than I.E. Irodov's Problems in General Physics. Now, if you've ever studied physics or engineering, you probably just felt a little jolt. This book is absolutely legendary for its tough problems that really force you to think. It's kind of like a rite of passage. And today, we're taking on one of its best. So here's the mission, straight from the book. Problem 1.208. We've got two jobs to do. First, we have to prove that a planet's total energy, its motion energy plus its gravity energy, only depends on the size of its orbit, which we call A, the semi-major axis. And second, we actually have to find the formula for that energy. And here's our game plan for how we're going to solve it. First, we'll set up what makes this a puzzle in the first place. Then, we'll grab the physics tools we're going to need. After that, we'll talk about a really smart strategy to make the math way easier. Then we'll actually do the math. And finally, we'll unpack what the result really means. It's a solid path to the solution. Okay, first up, the elliptical orbit puzzle. This really gets to the core of why this problem is so cool. I mean, just picture it for a second. A planet is jipping around the sun in an ellipse. It's constantly speeding up when it gets close, and then it slows way down as it swims far away. Its distance is changing every single second. So its kinetic energy is all over the place, and its potential energy is all over the place. The whole thing feels so dynamic. So the big question is, how on earth can all that craziness boil down to depending on just one single unchanging number? That's the puzzle. To solve this, we don't need any wild, exotic physics. Nope, we just need two of the most fundamental, most powerful tools in all of mechanics. Tool number one is the law of conservation of energy. The total mechanical energy, we'll call it E, is just the sum of the kinetic energy from its motion and the potential energy from gravity's pull. And the key thing here is that in a closed system like this, with no friction or anything, that total value E is locked in. It never ever changes, no matter where the planet is in its orbit. Our second tool is the law of conservation of angular momentum. You can kind of think of this as the rotational version of regular momentum. For our planet, because the sun's gravity is pulling it straight toward the center, there's no sideways push, no twisting force, or what physicists call a torque. And because there's no torque, its angular momentum, L, also stays perfectly constant the whole time. So why these two laws specifically? It all comes down to the nature of gravity itself. Gravity is a central force, meaning it always pulls toward one single point, the sun. That's why angular momentum is conserved. And it's also a conservative force, which means no energy gets lost or wasted as heat or friction. That's why mechanical energy is conserved. Boom, those two facts are the keys to everything. All right, so we've got our tools. Now for the really clever part. Section 3, the strategy. This is where you separate the pros from the rookies. It's not just about knowing the laws. It's about knowing where and when to use them. And this is a super common trap. This is where a lot of people get stuck. If you try to apply these laws at just some random point in the orbit, the math becomes an absolute nightmare. The velocity is at some weird angle to the radius, and you're suddenly drowning in sines and cosines. It's a mess. So here's the pro gamer move. We're going to be strategic. We'll analyze the orbit at the two most special, simplest points. First, the perihelion, that's the closest point, where the planet is moving its fastest. And second, the aphelion, the farthest point, where it's moving its slowest. And here's the magic trick. At exactly these 2 points, the velocity is perfectly perpendicular at a 90-degree angle to the line connecting the planet and the sun. And that little fact makes the math so much easier. So that gives us a really simple 2-step plan. Step 1, we're going to write our 2 conservation equations, one for energy, one for angular momentum, comparing the situation at perihelion to the situation at aphelion. Step 2, we'll have a system of 2 equations, and we'll just use algebra to solve them and find our expression for E. That's it. And that brings us to section 4. Time to roll up our sleeves and actually get this done. Let's do the math. First up, let's use conservation of angular momentum. We know that the angular momentum is constant, right? So the angular momentum at the closest point, m times v1 times r1, has to be exactly equal to the angular momentum at the farthest point, m times v2 times r2. That's our first equation, nice and clean. Second, let's use conservation of energy. Same logic. The total energy E doesn't change. So the kinetic plus potential energy at the close point has to equal the kinetic plus potential energy at the far point. That gives us our second equation. It looks a little more involved, but the idea behind it is just as simple. Okay, now for the algebra. Let's be really clear about what our goal is here. We have two equations, and we want to mash them together to get rid of the individual speeds and distances, the v's and the r's. We want to end up with an expression for E that only involves physical constants, and that one special number, A, the semi-major axis, which is just the average of the closest and farthest distances. Now, we're going to skip the page of algebraic gymnastics here, but after you substitute and solve that system of equations, you end up with something really quite beautiful. And that brings us to the payoff, our final section, the meaning of the result. Because getting the formula is one thing, but understanding the physics is what it's all about. And there it is. That's our answer. The total energy E equals negative gamma times the mass of the sun times the mass of the planet, all divided by 2 times the semi-major axis A. And just to be sure, if we check the answer key in Irodov, yep, we nailed it. But like I said, just getting the right answer isn't really the point. What does this simple, elegant formula actually tell us about the universe? What are the physical truths hiding in the math? Let's break it down. There are 3 huge takeaways here. First, that negative sign is incredibly important. It tells us the system is bound. The planet is trapped in the sun's gravity well. It doesn't have enough energy to escape. Second, here's the answer to our original puzzle. The energy depends only on A, the size of the orbit, not its shape. A long, skinny ellipse and a perfect circle with the same semi-major axis have the exact same total energy. And third, a larger orbit means a larger A, which makes the total energy less negative, which means it's higher. That makes total sense, right? You have to add energy to a satellite to boost it to a higher orbit. So the ultimate takeaway here is just how incredibly powerful conservation laws are. They act like a shortcut. They let us completely ignore the messy, moment-to-moment changes of the orbit. And by being clever about where we choose to look, we can transform a really complicated dynamics problem into a piece of elegant, solvable algebra. And that is a truly fundamental and beautiful idea in physics.